This episode is sponsored by Audible. Can reality be adjusted after events have occurred? That's the unsettling implication of the delayed choice quantum eraser experiment. We recently talked about the weird results of the single particle double slit experiment. They imply some startling things about the nature of reality. Today, I want to talk about an additional, possibly even stranger version of this experiment, whose results force us to reconsider the nature of causality itself. Now, this episode isn't going to make a lot of sense unless you've seen the first one, so go ahead and watch it if you haven't already. I'll wait right here. Okay, so the single particle double slit experiment suggests that things may not exist as well-defined, even real particles in that strange interim between creation and detection. There's a fuzzy space in which we don't know the particle's location or path. The Copenhagen interpretation would tell us that in this space, a particle is only its wave function, a distribution of possible properties. It's a probability wave that does all the usual wave-like stuff, like making interference patterns, until something happens to collapse it. At that point, the Copenhagen interpretation tells us that a true transition happens between wave and particle. But is that right? And if so, what really causes this transition? Does observation of the particle's location force the universe into settling down and deciding which particular reality we happen to be in? To head off any wild metaphysical giddiness, I want to say right now that there's absolutely no reason to believe that observation by a physicist is better at collapsing wave functions than observation by an electronic detector, or a houseplant for that matter. We'll talk about what observation really means at a later point. But it's still pretty interesting to see what happens if we try to observe the wave function at different points in the double slit experiment. The great mystery of the experiment is that very particle-like things appear to traverse both slits simultaneously, like you might expect of a wave. Physicists love a good mystery, and so have tried very, very hard to peek to see which slit these particles actually travel through before they produce the famous interference pattern. Turns out the universe is onto us. Any experiment that determines unambiguously which slit the particle traverses destroys the interference pattern. Instead, particles land in simple clumps, one for each slit, as though they were traveling as simple particles the whole time. This is even true if you place detectors on the far side of the slits, after the wave particle thing should have already been interfering with itself. It's like the wave function is collapsing retroactively, as if the universe is saying, okay guys, the human figured out which way you went, no more funny stuff, better pretend like you were particles that whole time. But there's a huge problem with this interpretation. It's impossible to make these measurements without messing up the wave. The interference pattern happens because the waves emerging from each slit are what we call coherent, which is a fancy way of saying that the relationship between the waveforms emerging from the two slits, so the locations of peaks and valleys, is predictable and stays consistent as the waves move forward. This coherence is what allows the waves to produce the interference pattern in the first place. But when you place some device in the path of either wave, you mess with this coherence, and so affect the pattern that reaches the screen. By the way, the double slit experiment where you try to determine which slit is traversed is called a which way experiment. And if the test is done on the far side of the slits, it's called a delayed choice experiment. Physicists hate being outsmarted by the universe, so they've come up with clever ways to measure which way the particle travelled while still preserving coherence. I'm going to talk about the most famous, performed in 1999. This experiment made use of a very special type of crystal that absorbs an incoming photon and creates two new photons, each with half the energy of the original. These new photons are twins of each other. In fact, they're an entangled pair, so fundamentally connected in strange ways that we'll come back to. So, place this crystal in front of the double slit to make coherent entangled pairs of any photons passing through. Send one of each pair off to the screen to produce our interference pattern, and use the other to figure out which slit the original photon passed through. Let's focus on detectors A and B here. Detector A lights up if the original photon passed through slit A, and detector B lights up for slit B. If we run this for a bunch of photons, we see that whenever detectors A or B light up, we get a simple pile of photons here at the screen. No interference pattern at all. It's as though any knowledge of which way the original photon travelled stops it from acting like a wave during its passage through the slits. And crazier, this experiment was set up so that photons reach A or B after their twins reach the screen. So, a photon lands on the screen according to the pattern defined by its wave function, and then later, its entangled partner reaches detector A or B and somehow retroactively influences the previous landing position. It's like the second photon is saying, whoa, 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 someone figured out which slit I came through, you better look like you came through that one too. This is amazing. And given that we only interact with one of the entangled pair, surely that means we aren't messing with the other, so we aren't ruining the interference pattern with decoherence. Could it get any weirder? This is quantum mechanics, so yeah. This extra stuff is the quantum eraser. Its job is to destroy any information about the path of the photons. These devices are beam splitters, just half-silvered mirrors. They work by allowing 50% of the photons through while reflecting the other 50%. Now, you have a new possible outcome. Instead of being reflected to detectors A or B, half of the photons end up in detectors C or D. But this clever arrangement ensures that if C or D light up, we have no idea which slit that photon came from. If we only look at the photons whose twins end up at detectors C or D, we do see an interference pattern. It looks like the simple act of scrambling the which way information retroactively sends the message, okay, chill, the observer lost the info of which slit we went through, it's safe to have gone through both again. Are we forced to double down on the interpretation that observation of the path causes the collapse of the wave function, and that the wave function can collapse all the way back to wherever our new knowledge extends to in the past? Some sort of retroactive reality cascade? This is a pretty wild story. For that reason, it makes sense to be cautious, even of the Copenhagen interpretation. Part of the appeal of the Copenhagen interpretation is that it avoids any physical interaction that moves faster than light. See, when a spread out wave function resolves itself into a set of known properties, say the location of a particle on the double slit screen, somehow the entire wave function knows to do this, to collapse at the same instant. But if these wave functions aren't physical, as the Copenhagen interpretation would tell us, then there's no real instantaneous physical interaction. By contrast, a physical interpretation of the wave function, like the de Broglie-Bohm pilot wave theory, requires an underlying physicality, a set of defined properties that evolves with the wave function, so-called hidden variables. That's a bit uncomfortable, because to explain experimental results, those physical properties need to act and change instantly at any distance. They need to have what we call non-locality. Now, the delayed choice quantum eraser double slit experiment doesn't tell us whether the wave function is physical or not, but it tells us that the Copenhagen or any other metaphysical interpretation of the wave function is no less, well, crazy sounding than a physical interpretation. In fact, the solution may lie in this fascinating phenomenon of quantum entanglement. As we'll see in the future, entangled particles really are able to influence each other instantaneously, and we'll see that their non-locality doesn't violate causality. So perhaps they can even affect coherence and decoherence retroactively and physically without making a causal mess. Perhaps this thing we call observation is just entanglement between the observer and the experiment. Perhaps the evolving tapestry of entanglement, in all its impossible complexity, is what really defines reality in this space-time. This episode of SpaceTime is supported by Audible.com. Right now, Audible is offering SpaceTime viewers a 30-day trial period. Check out audible.com/spacetime to access their audio programs and titles. I recently listened to The Big Picture by Sean Carroll. It's rare to find a brilliant theoretical physicist who's willing and able to discuss the philosophical and human implications of the science without the nonsense mysticism. Go to audible.com/spacetime and make sure you use that link so they know we sent you and to get a membership trial. Last week, Neil Stephenson came on the show to help us figure out how to save humanity from the end of the world. You guys had your own ideas. Masaya Kitsune asks, what if a black hole was headed towards the Earth? Could we stop it? This is a great end of world scenario, and the short answer is no. Long answer, depends on the type of black hole and how close it gets. The only black holes that we know for sure are buzzing around our galaxy are stellar remnant black holes, and are at least several times the mass of the Sun. Something like that passing through the solar system, even if nowhere near the Earth, would probably disrupt planetary orbits and either rearrange or scatter our planetary system. Even if it passed by the outer reaches of the solar system, it would perturb the Oort cloud and send swarms of comets plummeting inwards. However, there's a theoretical type of black hole, so-called primordial black holes, which may have formed in the first instance after the Big Bang. These may have masses similar to planets rather than stars, if they exist. And one of these passing through the solar system would only be dangerous if it was moving slowly enough, and if it came very close to the Earth. In fact, impact by a primordial black hole was one of the hypotheses that Seven-Eve's scientists proposed for the Moon's inexplicable destruction. T.S. Joe and Cinema would like to know what would exactly happen if a gamma-ray burst hit the Earth. I'm glad you asked. By happy coincidence, the wonderful channel Kurzgesagt recently published a whole episode on gamma-ray bursts. I'll let them answer this one for you. Check the link. A few of you pointed out that I neglected to mention certain known ends of the world that are coming in the distant future. And yeah, sure, Earth is certainly doomed. The increasing temperature of the Sun will cause all of Earth's oceans to evaporate in a billion years, plus or minus, depending on the model. But that's the sort of predictable event that hopefully a super advanced post-humanity can deal with a bit of basic geoengineering, increasing atmospheric reflectivity, for example, which is something we could do in the very near future if we wanted to. As for the death of the Sun and Andromeda's collision with the Milky Way, okay, let's deal with one end of the world at a time, people. I also asked you to submit your ideas for extinction-proofing humanity. The prize? A place on the Ark. Here are the winners. In the event of end of world, you guys should show up at your local spaceport. Your names will be on the door list. Error 404, heard or not found, had a great idea in which you collect asteroids and put them in orbit around the Earth, ready to sling at any oncoming impactors before they reach us. This is actually a really nice one. The rocks don't even have to be all that big. As long as you spot the incoming rock on one of its near-Earth passes before the impact pass, you could play a little cosmic billiards to knock it just off course. Timac TR suggests we upload our minds into deep underground computers. Go full virtual? I'm down with that. Although who's to say we didn't already do that? Caleb Tandberg wants to build underwater cities instead of underground cities to protect against gamma-ray bursts. I really love this idea. You don't even need much water at all to fully protect us from the gamma-ray burst or the subsequent UV, so just below the surface is great. All surface life is laid waste, but hey, the deathless face of the unborn mind has an extinction-proofing idea. Reinvent our monetary economic systems to produce efficient, stable and healthy societies that actually have the energy and collective intelligence to progress technologically. Okay, well if you're going to be sensible about it, but can we please still have the underwater cities? This episode is sponsored by Audible. Wouldn't it be nice to be everywhere at once? According to quantum mechanics, you are. At least a little bit. Quantum mechanics is a spectacularly weird theory. One of its basic tenets is that certain properties of an object are fundamentally uncertain. They don't hold well-defined values, but instead must be described as a distribution of possible states of being. Each specific state has a certain probability of being true when the object is observed. Or more accurately, until a quantum object interacts with something, all possible states are just as real as each other. Although not necessarily equally likely, there's a distribution of probabilities for each of an object's quantum properties. That distribution, and the way it changes over time, is coded in the object's wave function. The reduction of a fuzzy possibility space into a specific measurable property is sometimes referred to as the collapse of the wave function. We'll talk a lot more about this awesome weirdness in the future. For now, let's just look at the strange consequences of quantum uncertainty in an object's location. This is one of the early realizations in the development of quantum theory. French mathematician and physicist Louis de Broglie figured out that any material object is really a matter wave. It can be described as a wave packet of position probability, and that wave packet has a wavelength. This de Broglie wavelength defines how well determined an object position is. A large wavelength means a highly uncertain position. A small wavelength means a well-defined position. That's true of subatomic particles, and it's sort of true of anything. Right now, I'm mostly right here, but there's also a smaller chance that I'm here, here, or here. There's an infinitesimal chance that I'm on the moon. Observe me and you'll collapse my wave function, and probably find me pretty much exactly where you expect to. See, an object's de Broglie wavelength depends on its momentum, so mass times velocity. Higher momentum means a smaller wavelength. In fact, it's the minuscule Planck constant divided by momentum. Humans are made up of several tens of kilograms of thermally moving particles and have de Broglie wavelengths a couple of orders of magnitude smaller than the Planck length. You're everywhere in the universe, but not very much. You're as right there as it's possible to be. But what about something much smaller? Say, a tightly bound bundle of 2 protons and 2 neutrons that we call an alpha particle. On its own, this would be a helium nucleus. But these bundles also exist as parts of heavier atomic nuclei. There, an alpha particle is snugly bound into the nucleus by the strong nuclear force. We can imagine an alpha particle as being like a ball trapped in a steep valley of potential energy. It can roll around inside, but unless it has a very large kinetic energy, it will never roll over the edges. But quantum objects aren't at all like balls. Their positions are not well defined. As an alpha particle approaches the force barrier of the nucleus, its wave packet is reflected backwards. Usually. See, that wave packet describes a range of possible locations for the approaching particle. But that possibility space does not end suddenly at the force barrier. Instead, it drops off quickly, exponentially, through the steep walls. However, it never quite reaches zero. There remains a tiny tail of probability outside the nucleus, beyond the reach of the strong nuclear force. That means there's a very tiny chance that instead of bouncing off the wall, the particle will, at the last minute, resolve its position in that unlikely outside bit of its possibility space. That looks like the particle teleporting out of the nucleus. This process is called quantum tunneling. When it's an alpha particle escaping a nucleus, this is one of the most important mechanisms for radioactive decay. Quantum tunneling also goes in the other direction. Protons, neutrons, electrons, and alpha particles can quantum tunnel into nuclei in various types of fusion and particle capture phenomena. In fact, without quantum tunneling, stars could not fuse hydrogen into heavier nuclei. A variety of modern electronics also rely on the tunneling phenomenon. including the transistor. But how quickly does the alpha particle move through this barrier? Well, as far as we know, it's instantaneous. That suggests a velocity faster than light, which sounds problematic. It's actually extremely hard to test this because we can't make clocks accurate enough to time such a ridiculously quick event. Here's one way you might test this. Remember the LIGO interferometer that discovered gravitational waves? Laser beams are sent down paths at right angles and then brought back together. The photon wave packets interact with each other and produce an interference pattern that is incredibly sensitive to differences in path lengths. Well, that's a Michelson interferometer, but let's change the arrangement a bit. We want to send individual photons instead of lasers, and we want to block one of the paths with a very thin reflective barrier, like this. In the absence of quantum tunneling, that barrier should reflect its photon 100% of the time. But just like with the alpha particle, as the photon approaches the barrier, the wave packet defining its possible location extends weakly beyond the barrier. About 99% of the time the photon is reflected, but 1% of the time it will resolve itself beyond the barrier and it'll continue on its path. If those rare tunneling photons really do travel instantaneously through the width of the barrier, then they should arrive at the detector slightly ahead of the photon that travels the unimpeded path. That will be apparent when their wave packets don't line up perfectly at the other end. But for this to work, the original path lengths of the interferometer need to be very precisely equal. To make that work, you need to use a second and perhaps even weirder feature of quantum mechanics: quantum entanglements. That is a huge topic for another video. It offers another tantalizing hint at faster than light influences. For now, let me just say that in order to produce these entangled states, the path length of the interferometer needs to be identical to very high precision. Tune the path lengths until the weird effects of entanglement emerge, and you know that they're equal. At that point, you can get an incredibly precise measurement of any differences in photon travel time. A team of very clever physicists have successfully performed this experiment. Reference link below. What did they find? The tunneling photon does arrive a tiny bit earlier than its partner. It appears to teleport through the barrier and so travel faster than light. Sweet! So scale up from photons to people and we have transporter beams, right? Well, this apparent violation of relativity only occurs deep within the quantum realm. A particle resolves its location anywhere within the vicinity of its de Broglie wavelength. That uncertainty in location allows tunneling. But even without a barrier, this location fuzziness leads to uncertainty in the arrival time of the photon. An unimpeded photon could arrive at the earlier time of the tunneling photon because its wave packet includes that in its range of possible positions. When you add the barrier, all you're really doing is reshaping the wave packet, selecting only the possibility space of early arrival. This can look like an increase in the speed of light, but only within the uncertainty range defined by the de Broglie wavelength. More accurately, it's within the uncertainty range defined by the Heisenberg uncertainty principle, which is perhaps the deeper principle from which the de Broglie wavelength comes. This is something we'll also get back to in detail. Any macroscopic object is subject to a very well-defined speed limit, but in the quantum realm, Heisenberg uncertainty does seem to allow instantaneous motion, and even perhaps causality violation within quantum limits. Stay tuned for the implications of this on both quantum and cosmic scales of space-time. This episode of SpaceTime is supported by Audible.com. Right now, Audible is offering SpaceTime viewers a 30-day trial period. Check out audible.com/spacetime to access their audio programs and titles. One book that I read recently is How the Universe Got Its Spots by Janna Levin. It lays out some amazing ideas connecting our universe's topology and extent to the spots in the cosmic background radiation. Throw in some string theory and black holes and a really unique writing style, and it's a very insightful pop-sci book. Go to audible.com/spacetime and make sure you use that link to help us out and to get a membership trial. Hey guys, there was a glitch that stopped last week's episode getting into your subscription feeds. If you didn't see our episode on the astrophysics of ice ages, go check it out. I'm going to respond to comments next week to give you all a chance to see it first. In that episode, we'll also be giving the solution to the Dark Energy Challenge question, as well as telling you about some pretty amazing news from the Large Hadron Collider. A few weeks ago, some very excitable science journalists were plastering the internet with headlines like "Fifth Fundamental Force of Nature Discovered." What was that all about? Is there really a new force? Can I finally get my X-Wing out of that swamp? Let me make it sound a little less hyped. There was something slightly weird about how a bunch of beryllium atoms were acting that told physicists that for a tiny fraction of a second, an unknown particle may have existed. Alright, let me make it sound a little more hyped, but also a lot more specific. Atomic nuclei have energy levels, just like their electron shells do. Protons and neutrons can occupy excited states, contain excess energy, and when they settle down again they give off that energy as photons, but also sometimes as a particle or a particle-antiparticle pair. One thing that comes out of a pile of beryllium-8 atoms is a lot of electron-positron pairs. They can pop out at a lot of different energies. Researchers noticed a slight excess in their energies at 17 mega-electron volts. It's as though something with a mass energy equivalence of 17 MeV was decaying into those particles. Now this might sound a little bit familiar. The same sort of excess in the photons emitted after proton collisions in the Large Hadron Collider led to the discovery of the Higgs boson. Just recently, a new, very slight excess at the LHC was originally thought to be a new particle, but was discovered to have been a statistical fluke. But this excess in the beryllium-8 decay is not slight. It's now a 6.8 sigma excess, which is statisticese for it being pretty darn certain that something weird is going on. But why do they think that the mysterious 17 MeV particle is a new type of fundamental force? Well, in short, it's because the anomaly was observed for a very particular transition between the beryllium nuclear states. That transition meant a difference in energy, but also a difference in some other quantum stuff, spin parity and isospin. And the easiest way to explain this is if a spin 1 gauge boson was created. Such a particle would be a mild extension of the standard model. Not too crazy, but certainly brand new physics. Yes, a new spin 1 gauge boson. No, seriously, this is awesome if it's true. See, 3 of the 4 fundamental forces, electromagnetism and the strong and weak nuclear forces, are all communicated by these gauge boson things. A new gauge boson means a new fundamental force. Why are we only spotting this thing now? Well, the standard wisdom for finding new particles is to create higher and higher energies, hence the Large Hadron Collider. Any particle capable of existing at lower energies should have been spotted. But that's not true if the particle is a ninja. By that I mean dark to electromagnetism and generally interacting with regular matter very little. If that's the case, it could be produced at much lower energies than the giga-electron-volt energies produced in the LHC, like the mega-electron-volt transitions of atomic nuclear energy levels. If the decay product of such a transition is very weakly interacting, these particles could be everywhere and we wouldn't know it. Like ninjas. And like dark matter. In fact, this is a tantalizing possibility. Not that dark matter is ninjas, although as a scientist I'd need to test that before I ruled it out. No, I mean that this new particle may have something to do with dark matter. It's very weakly interacting, but the researchers suggest it could mediate interactions between the so-called dark sector and the visible universe. Okay, on to the solution to the quantum eraser challenge. To summarize, I asked you to tell me why it's impossible to send any real data back in time using the delayed choice quantum eraser experiment, and so cheat on the lottery. Remember, the landing location of each individual photon passing through to the interference screen of this experiment does seem to be influenced by a decision that is made regarding each of those photons' entangled partners in the future. That decision was whether we would know the path of the original photon, thus eliminating an interference pattern, or to erase our knowledge of that path, which brings the interference pattern back. That decision is made randomly by a beam splitter in the original experiment, but it's conceivable that the experiment could be adjusted so that a person could make the decision. So why can't I send winning lottery numbers back to myself? The reason is that there's absolutely no way to tell if any given photon at the interference screen has a known path until you compare the results of the screen with the results at the detector. In fact, the distribution of photons at the screen always looks like a single blurred distribution. There's no visible interference pattern at all. It's only when you flag which photons had twins arriving at detectors A, B, C, or D that you see patterns arise. In fact, even if you remove all of the A and B photons, you still don't see an interference pattern until you distinguish C versus D. And this is because those photons have interference bands that are exactly out of phase. The peaks of C line up with the troughs of D, and together they look like the same sort of blur you get if you combine A and B. This is pretty insane. The photon positions are decided, and presumably those patterns are embedded in the distribution. Those embedded patterns are set by the eventual destination of the entangled partners of those photons, but the distribution may be in place long before those twins finish their journey. Yet we can't extract the patterns of the photons that landed at the screen until we get the information of which detectors their entangled twins hit. That information can't travel backwards in time or faster than light. So unfortunately, this means the information about the winning lottery numbers remain embedded in the pattern and lost to us until after the numbers are drawn. If your name appears below, you got this right and described your reason well. You guys should email your names, addresses, US t-shirt sizes, so small, medium, large, etc., to pbsspacetime@gmail.com. Also let us know which of these t-shirts you want. We'll send it right out to you. For the rest of you, you can still grab a Spacetime t-shirt of your very own via the link in the description. Okay, that's the answer. But there's still time for a mini rant about the role of consciousness in quantum mechanics. The delayed choice in this experiment is whether or not to know the path of the original photon, or whether to erase that knowledge. But don't take this too literally. We don't need to invoke conscious knowledge to explain the results. If either detectors A or B are triggered, then there's an asymmetry in the global wave function passing through one slit versus the other, and this can lead to decoherence. Admittedly, this decoherence appears to affect the wave function at times before the apparent cause of the decoherence, but this doesn't end up violating causality, and so it's way less out there than photons somehow knowing that in the future some conscious mind will know its path. Frankly, it's all just so weird. And amazing. Amazing enough without inventing mystical interpretations that somehow give us psychic wave function collapsing powers, as much as we'd all like to believe we have them. Nonetheless, there is a clue, somewhere in all this weirdness, to the fundamental workings of space-time. There is one interpretation of the meaning of quantum mechanics that somehow manages to skip a lot of the wildly extravagant or near mystical ideas of the mainstream interpretations. It's the de Broglie-Bohm pilot wave theory. And despite its alluringly intuitive nature, for some reason it remains a fringe theory. Misinterpretation of the ideas of quantum mechanics has spawned some of the worst quackery pseudoscience, hoo-ha, and unfounded mystical storytelling of any scientific theory. It's easy to see why. There are some pretty out there explanations for the processes at work behind the incredibly successful mathematics of quantum mechanics. These explanations claim stuff like things are both waves and particles at the same time, the act of observation defines reality, cats are both alive and dead, or even that the universe is constantly splitting into infinite alternate realities. The weird results of quantum experiments seem to demand weird explanations of the nature of reality. But there is one interpretation of quantum mechanics that remains comfortably, almost stodgily, physical. That's de Broglie-Bohm pilot wave theory. Pilot wave theory, also known as Bohmian mechanics, stands in striking contrast to the much more mainstream ideas of, for example, the Copenhagen and many worlds interpretations. Now, we've covered both of those before, and those episodes are really worth a look. Pilot wave theory is perhaps the most solidly physical, even mundane, of the complete and self-consistent interpretations of quantum mechanics, but at the same time it's considered one of the least orthodox. Why so? Because orthodoxy equals radicalism plus time. And the founding fathers of the Copenhagen interpretation of quantum mechanics, Niels Bohr and Werner Heisenberg, were radicals. When quantum theory was coming together in the 20s, they were fervent about the need to reject all classical thinking in interpreting the strange results of early quantum experiments. One aspect of that radical thinking was that the wave function is not a wave in anything physical, but an abstract distribution of probabilities. Bohr and Heisenberg insisted that in the absence of measurement, the unobserved universe is only a suite of possibilities of the various states it could take were a measurement to be made, and that upon measurement, fundamental randomness determines the properties of, say, the particle that would emerge from its wave function. This required an almost mystical duality between the wave and particle-like nature of matter. Not everyone was so sure. Einstein famously hated the idea of fundamental randomness, but to counter Bohr and Heisenberg, there needed to be a full theory that described how a quantum object could show both wave and particle-like behavior at the same time without being fundamentally probabilistic. That theory came from Louis de Broglie, the guy who originally proposed the idea that matter could be described as waves right at the beginning of the quantum revolution. De Broglie's theory reasoned that there was no need for quantum objects to transition in a mystical way between non-real waves and real particles. Why not just have real waves that push around real particles? This is pilot wave theory. In it, the wave function describes a real wave of some stuff. This wave guides the motion of a real point-like particle that has a definite location at all times. Importantly, the wave function in pilot wave theory evolves exactly according to the Schrödinger equation. That's the equation at the heart of all quantum mechanics that tells the wave function how to change across space and time. This means that pilot wave theory makes the same basic predictions as any other breed of quantum mechanics. For example, this guiding wave does all the usual wavy stuff, like form an interference pattern when it passes through a pair of slits. Because particles follow the paths etched out by the wave, it'll end up landing according to that pattern. The wave defines a set of possible trajectories, and the particle takes one of those trajectories. But the choice of path isn't random. If you know the exact particle position and velocity at any point, you could figure out its entire future trajectory. Apparent randomness arises because we can't ever have a perfect measurement of initial position, velocity, or other properties. But this hypothetical predictability means that a pilot wave universe is completely deterministic. When de Broglie presented his still incomplete theory at the famous Solvay conference of 1927, it didn't go down so well. Technical objections were raised, and Niels Bohr doubled down on the probabilistic interpretation. De Broglie was convinced, and he dropped pilot waves altogether. The idea was forgotten for decades, and Copenhagen became the orthodoxy. It took until 1952 for another physicist, David Bohm, to feel very uncomfortable with some of the wackiness of Copenhagen and to rediscover de Broglie's old idea. Bohm took up where de Broglie left off and completed the theory. The result was Bohmian mechanics, also known as de Broglie-Bohm pilot wave theory. These days, more and more serious physicists are favouring Bohm's ideas. However, it's far from being broadly accepted. De Broglie himself remained firmly in the Copenhagen camp even after Bohm's efforts. See, although pilot wave theory makes all of the usual predictions of quantum mechanics, it has some really fundamental differences. Those differences are in the sort of special thinking you need to do in order to accept pilot waves over other interpretations. In fact, most of the arguments for or against it are about this special thinking. Are you more or less comfortable with the oddness of pilot waves versus the oddness, say, of Copenhagen or many worlds? So what uncomfortable thinking does pilot wave theory require? Well, for one thing, it needs a teensy bit of extra math that mainstream interpretations don't. As well as the Schrödinger equation that tells the wave function how to change, it also has a guiding equation that tells the particle how to move within that wave function. That extra math is considered unparsimonious to some, a needless added complexity. However, the guiding equation is derived directly from the wave function, so some would argue that it was there all along. A more troubling requirement of Bohmian mechanics is that it does contain real complexity that is not encoded in the wave function. That's something that Niels Bohr was so fervently against. Bohmian mechanics has so-called hidden variables, details about the state of the particle that are not described by the wave function. According to pilot wave theory, the wave function just describes the possible distribution of those variables given our lack of perfect knowledge. But hidden variables have a bad rap in quantum mechanics. Pretty soon after de Broglie first proposed pilot waves, the revered mathematician John von Neumann published a proof showing that hidden variable explanations for the wave function just couldn't work. That proclamation contributed to the long shelving of pilot wave theory. But in fact, von Neumann didn't quite get the full answer. It turns out that the restriction against hidden variables only applies to local hidden variables. So there can't be extra information about a specific region of the wave function that the rest of the wave function doesn't know. This was figured out pretty soon after von Neumann's paper by German mathematician Grete Hermann, although her refutation wasn't noticed until it was rederived by John Bell in the 1960s. This helped the resuscitation of pilot wave theory, because Bohmian mechanics doesn't use local hidden variables. Its hidden variables are global. The entire wave function knows the location, velocity, and spin of each particle. This non-locality is another weird thing you have to believe in order to accept pilot waves. Not only does the entire wave function know the properties of the particle, but the entire wave function can be affected instantaneously. So a measurement at one point in the wave function will affect its shape elsewhere. This can therefore affect the trajectories and properties of particles carried by that wave, potentially very far away. But quantum entanglement experiments show that this sort of spooky action at a distance is a very real phenomenon. Again, we've gone into the non-locality of entangled particles in detail before, also worth a look. It's a tough idea to swallow, but experiments indicate that some type of non-locality is real, whether or not we accept pilot waves. It would be remiss of me to talk about pilot waves without mentioning the amazing analogy that was discovered in bouncing droplets on a vibrating pool of oil. I'll let Veritasium cover this one in detail. It's pretty amazing. But we see many of the familiar quantum phenomena appear in this macroscopic system of a suspended oil droplet following its own pilot wave. Now, we shouldn't take a macroscopic analogy as proof of microscopic reality, but it certainly demonstrates that this sort of thing does happen in this universe, at least on some scales. I should probably also add that de Broglie pilot wave theory is certainly wrong. And I don't think anyone could deny that because it doesn't account for relativity, either special or general. That means it's at best incomplete. While regular mechanics has quantum field theory as its relativistic version, pilot wave theory hasn't quite got there yet. Quantum field theory pretty explicitly requires that all possible particle trajectories be considered equally real. Pilot wave theory postulates that the particle really takes a single actual trajectory, the Bohm trajectory. This is not consistent with quantum field theory, and so there isn't a complete relativistic formulation of Bohmian mechanics yet. But there is good effort in that direction. Now let's not even start talking about gravity. No version of quantum mechanics has that sorted out. Also, we can't ignore the fact that the initial motivation behind pilot wave theory was to preserve the idea of real particles. And I think we need to be dubious about that sort of classical bias. All that said, pilot wave theory does do something remarkable. It shows us that it's possible to have a consistent interpretation of quantum mechanics that is both physical and deterministic. No hoo-ha needed. Maybe something like pilot waves really do drive the microscopic mechanics of space-time. Hey guys, so we recently launched our Patreon page, and I want to thank those of you who've contributed so far. This is really going to be a huge help, and it's going to be a lot of fun. I've loved the discussions we've been having on the EM drive and future episode ideas. Not so much the embarrassing quark compilation. Damn you, Louis. Anyway, if you're interested in supporting the show, heading over to the Patreon page would be an amazing way to do that. Or just keep watching. In our last episode, we talked about the strangest of stars, the strange star, aptly named. Your comments by comparison were very reasonable. Burak asks why quark/strange matter isn't found naturally in the universe, given that it's supposed to be so stable. Okay, so the hypothesis is that strange matter is the most stable matter in the universe, but this only applies when you have a large number of quarks mushed together. In that case, having one strange for every one up and one down quark is a very low energy state, and so is very stable. However, this doesn't work when there are only a small number of quarks, say in the typical atomic nucleus. In that case, any massive strange quarks will decay into the lighter up or down quarks. But during the quark era, the universe was full of this quark-gluon plasma, and the problem is that the universe at this time wasn't dense enough and was expanding too quickly for strange matter to form in any great abundance. That said, some strange matter may have formed during the quark epoch, and the resulting particles are called strangelets. They may be around today. Depending on the as yet unknown physics of strange matter, these strangelets may even be expected to be more stable the larger they are, and so would grow over time. In fact, such strangelets may even convert any regular matter they come into contact to into strange matter. Sebastian Lopez asks, how are the magnetic fields of neutron stars created? Well, to create and sustain a magnetic field, you need some sort of charge that's moving or spinning in some way. That might seem a problem for an object made up of neutral particles like a neutron star. However, a neutron star isn't only made up of neutrons. You have an outer crust of conductive iron that can support an enormous current of electrons. And below that crust, there's a region centimeters to meters deep in which you have significant impurities of electrons and protons mixed in with the neutrons, perhaps up to 10% electrons and protons by mass of the star. With their extreme rotation rates, neutron stars support electrical currents sufficient for magnetic fields of up to 100 million Tesla. And then you have magnetars, which are believed to get to 10 to the power of 11 Tesla. These fields are supported by superconduction of protons beneath the surface. The 757 Packer fan would like to know whether neutronium compares to adamantium. I see where you're going with this. Neutronium pretty much sucks as a skeleton graft for Wolverine. Firstly, it would weigh as much as a mountain range, which isn't helpful. Also, it's dense, but not necessarily strong. In a neutron star, it's a superfluid, so not ideal there, but at atmospheric pressure, or even inside Wolverine pressure, it would expand into a gas cataclysmically and the neutrons would decay into protons and electrons and an awful lot of radiation. A 5 centimeter cube of neutronium would explode with the equivalent energy of around 1 trillion hydrogen bombs. That's going to take some serious regeneration to recover from. By the way, this is why science is so important. This episode is supported by the Great Courses Plus. The Planck constant defines the size scale at which the familiar physics of our macroscopic reality gives way to the weirdness of the quantum world. You might not expect the quantum behavior of the microscopic to be observable on all scales of the universe, but it is. In fact, you can see the effect of this quantum behavior and even measure the Planck constant just by observing the color of sunlight. Zeno's famous paradox tells us that it's impossible to overtake a tortoise. Run as fast as you like. By the time you reach the tortoise's initial position, it'll have moved forward. Reach that second position, it'll have moved forward again. To overtake a tortoise, you need to travel to its previous position infinite times. Each of those steps is shorter than the last, but there are still an infinite number of them. There are a few problems with this paradox, but one is that it assumes that space is infinitely divisible. This is not true. As your distance to the tortoise becomes unthinkably small, there arises a quantum uncertainty in your location. Get close enough to it, and this quantum blurriness means it's impossible to say whether your location is really behind or in front of the tortoise. We talked about this recently when we discussed the de Broglie wavelength. This, and more formally the Heisenberg uncertainty principle, describes the smallest distance for which an object's location can be meaningfully defined. The tiny Planck constant at 6.63 by 10 to the minus 34 joules seconds sets the scale of this quantum blurriness. So it also sort of defines a pixel scale to reality. In many ways, it defines the divisibility of the quantum world. In fact, the Planck constant appears in essentially all equations that describe quantum phenomena. The Heisenberg uncertainty principle and the de Broglie wavelength, but also the Schrödinger equation, the energy levels of electron orbits, and importantly, the relationship between the energy and frequency of a photon. It also sets the size of the Planck length, which is, hypothetically, the length below which the concept of length loses meaning. It may define the scale of quantum reality, but the influence of the Planck constant can be seen even on our scale. For example, along with the sun's temperature, it sets the color of sunlight. If the Planck constant were 25% smaller, the sun would be violet, all else being equal. In fact, the mystery of why hot things glow the color that they do led us to discover the quantum universe in the first place. Science fact: everything in the universe glows with the light of its own internal heats. Heat is just the energy in the random motion of particles comprising an object. Accelerated charges produce electromagnetic radiation, light, and so an object made of jiggling charged particles, like electrons and protons, glows. The hotter an object is, the faster its particles jiggle, and so the average frequency of the resulting particles of light, of photons, increases with temperature. This average frequency defines the color that we see. The sun is yellow because its 6,000 Kelvin surface produces more photons in the greeny yellow part of the electromagnetic spectrum than anywhere else. The blue supergiant star Rigel is 12,000 Kelvin, and so it pumps out lots of high-frequency blue light and even more ultraviolet. Your temperature is around 310 Kelvin, so your heat glow is mostly in low-frequency infrared photons. It was Sir Isaac Newton who first analysed this heat glow in the 1660s when he used a prism to split sunlight into its component colours. But he didn't realise that the relative brightnesses of those colours held the key to the quantum world. By the late 1800s, the distribution of brightnesses with frequency produced by hot objects had been mapped in careful experiments that blacked out anything but the glow of heat. The resulting blackbody spectrum looks like a lopsided bell curve. However, the deep physics behind this shape remained a mystery. The key to unlocking the mystery lay in finding a mathematical description for the blackbody spectrum. At the beginning of the 20th century, a couple more Brits, Lord Rayleigh and Sir James Jeans, attacked the problem with a relatively new idea called the equipartition theorem. It states that an object's heat energy will end up jiggling all of its particles in all the ways that they can be jiggled. In physics speak, at equilibrium, energy is evenly spread between all possible energy states. This simple idea allowed our good Englishmen to figure out the frequencies of the photons produced by all of this thermal motion. The resulting Rayleigh-Jeans law described the blackbody spectrum perfectly. For low frequency, infrared light. But for higher frequencies, like visible and ultraviolet, it predicted brightnesses that were way too high. Worse, it predicted that the intensity should eventually approach infinity as frequency increased. It paints the crazy picture of a universe full of infinite extreme energy gamma radiation. This appears not to be the case. This was called the ultraviolet catastrophe. It was catastrophic because it meant that something was fundamentally wrong with the classical physics that went into the Rayleigh-Jeans law. The problem turned out to be that in classical physics, everything can be infinitely divided. There's no smallest anything. The Rayleigh-Jeans calculation allows particles to vibrate with any amount of energy, all the way down to infinitesimally tiny wiggles. When they tried to mathematically distribute heat energy, to equipartition it across possible energy states, way too much energy got packed into the countless, very tiny energy states at high frequencies. Mathematically, Rayleigh and Jeans were chasing Zeno's tortoise, infinitely dividing the smallest remaining energy states, and so never ever finding an end to them. German physicist Max Carl Ernst Ludwig Planck resolved the catastrophe almost by accident. While searching for a new mathematical approach to deriving the blackbody spectrum, he needed some sort of math trick to count those supposedly infinite energy states. In what he described as a moment of desperation, he tried something pretty silly. He decided that those particles could only vibrate with energies that were a multiple of some minimum energy. He quantized the energy states. He set this minimum energy to be the frequency of a particle's vibration times a very, very small number, a number that had yet to be measured. That number became the Planck constant. It was a move similar to smooshing your hands on the keyboard when your computer freezes. But it worked. It allowed Planck to equipartition energy in a way that solved the ultraviolet catastrophe. Why? Because it limited how much energy those high-frequency vibrations could hold. Planck's new equation described the shape of the blackbody spectrum exactly across all frequencies of light. It became Planck's law. Now, Max Planck didn't originally think that these quantized energy levels were real. It was supposed to be a math trick. He expected his new constant to turn out to be zero, which would mean no interval between energy states, no quantization, no minimum energy. In that case, the Planck constant would have cancelled out in the final equation. But it didn't. The Planck constant is firmly entrenched in the Planck blackbody law. Energy quantization is real. Now, the actual value of the Planck constant still had to be measured, but given a mathematical form for the blackbody spectrum, it was possible to do this just by varying the constant until the Planck law matched the observed spectrum. But once you know the Planck law and an object's temperature, you can calculate the Planck constant just by finding the brightest part of an object's heat glow. For example, by observing the colour of the sun. As usual, it took Albert Einstein to fully understand the physics behind Planck's strange quantized vibrations. Einstein realized that it's actually light that is quantized. Those little vibrating particles do have quantized energies, but it's because they can only gain or lose energy by absorbing or emitting one particle of light at a time. And that light comes in indivisible energy packets. Planck's discovery was the clue Einstein needed to hypothesize the existence of the photon, part wave, part particle, carrying a quantum of energy equal to the now familiar frequency of the wave times the Planck constant. Einstein proved this through the photoelectric effect. It got him the 1921 Nobel Prize in Physics, shortly following Planck's Nobel of 1918. These discoveries sparked a frenzy of sciencing that led to the quantum revolution of the 1920s. And that little number that Max Planck came up with in his moment of desperation, the Planck constant, remains at the heart of all things quantum. But not just quantum. By defining the shape of the blackbody spectrum, the Planck constant can be read in the colour of the sun and the stars, in the brightness of the different colours of the rainbow, and combined with a small handful of other fundamental constants, it governs the behaviour of everything in this space-time. Thanks to the Great Courses Plus for sponsoring this episode. The Great Courses Plus is a service that allows you to learn about a range of topics from Ivy League professors and educators from other schools around the world. Go to thegreatcoursesplus.com/spacetime and get access to a library of different video lectures about science, math, history, literature, or even how to cook, play chess, become a photographer. New subjects, lectures, and professors are added every month. With the Great Courses Plus, you can watch as many different lectures as you want, anytime, anywhere, without any tests or exams. Help support SpaceTime and start your 1-month trial by going to thegreatcoursesplus.com/spacetime. Last week we talked about gravitational lensing, and you guys asked all the good questions. Okay, a lot of you wanted to know why it is that the Einstein cross is a cross rather than a full ring. So if your light source, your lens, and your telescope are all perfectly lined up, and your lens is perfectly circular around the line connecting the three, the optical axis, then the light source will be stretched out into a circle. We call that an Einstein ring. In that case, all of the paths around the lens are equally good, and so light from the source can travel all of them. But perfect alignment is almost impossible for something as small as a quasar. The quasar is always slightly offset from the optical axis. Also, the lens mass distribution is never perfectly circularly symmetric around this axis. It's elongated in one direction or another. The result is that only a few paths around the lens get deflected directly back to us. If the alignment is still pretty close, then you see 4 images. In fact, there's really 5, 4 magnified images and 1 heavily demagnified image in the center that we can't see. On the other hand, if the light source is large, for example an entire galaxy, then it's easier for at least part of the galaxy to be located directly on the optical axis. Then you'll see an Einstein ring. There are some cases where you see 4 individual quasar images connected by an Einstein ring. That Einstein ring is actually the galaxy that hosts the quasar. Gary Palmer would like to know how we can really be confident measuring the mass of a gravitational lens, given we don't really know the composition of that lens. Well, it's true that for a given lens, there could be a range of different configurations of matter that produce the same distribution of light seen in the lens, so image positions and brightnesses. But if you know the distance to the light source and the distance to the lens, both from redshift, then you can explore an enormous range of possible lens mass distributions with computer simulations. So you end up with a set of virtual lenses that can reasonably produce the observations. That set will span a range of masses, but that range is usually pretty small. So we end up with a best mass and error bars defined by that range. Prasad Deshmukh and a few others asked, is the cosmic microwave background radiation gravitationally lensed? Actually, yeah, the CMB is affected by weak lensing, so all of its blobs are very slightly distorted. This can change the power spectrum, so the distribution of the sizes of its blobs, which is really important for measuring cosmological parameters. It can also potentially introduce B-mode polarizations. That's exactly the same type of swirliness that primordial gravitational waves should produce. So yeah, we're going to need to correct for lensing in the CMB. Ed Egermont wonders if gravitational waves are also subject to gravitational lensing. Well, yeah, gravitational waves are ripples in the fabric of space-time, so they have to go where the space-time goes. Dylan T tells us that he met his wife by suggesting that they space-time and chill. I'm glad we could help you guys get entangled. Is there a hidden physical reality that underlies the strange behaviour of the quantum world? Or is that reality an illusion in the eye of the observer? The weird phenomenon of quantum entanglement gives us quite startling clues to the answer. Babies may suck at math, but they're actually surprisingly good at quantum mechanics. Well, one fundamental aspect of it anyway. The peekaboo game is thought to be so hilarious to babies because they lack object permanence. Hide your face with your hands and a baby won't automatically assume that you kept existing. Reveal your face again and it's as though you popped into existence from nothing, which is of course a hilarious thing to do. Kids get over this pretty quickly as they learn that things don't magically pop into and out of existence for no reason. By the time they grow up and go to college to study physics, the notion of object permanence is so deeply embedded that we don't even bother teaching it in Physics 101. And yet the idea that the universe keeps existing when we're not looking at it is a pretty fundamental implied assumption behind all of classical physics. Indeed, most of science takes it for granted that the universe is real whether or not we're looking at it. This notion that the universe exists independent of the mind of the observer is called realism in physics. But quantum mechanics is so bizarre that it still has scientists wondering if we need to reject even this basic premise. This was the source of one of the most heated debates at the advent of quantum mechanics. On the one hand, Niels Bohr insisted that it was meaningless to assign reality to the universe in the absence of observation. In the intervals between measurement, quantum systems truly exist as a fuzzy mixture of all possible properties, what we call a superposition of states. In between observations, the wave function describing this superposition is a complete description of reality, and our experience of a well-defined material universe only has meaning at the moment of measurement. This peekaboo universe is the heart of Bohr's Copenhagen interpretation. On the other hand, Albert Einstein insisted on an objective reality, a reality independent of our observation of it. He insisted that the wave function, and by extension quantum mechanics, is incomplete. There must exist what we call hidden variables that reflect a more physical underlying reality. In an effort to demonstrate the silliness of Bohr's idea, Einstein, along with Boris Podolsky and Nathan Rosen, proposed a quantum scenario that showed that in order to abandon the assumption of realism, you also had to abandon a concept almost as sacred: locality. Locality is the idea that each bit of the universe only acts on its immediate surroundings. This is fundamental to Einstein's relativity, which tells us that the chain of cause and effect can't propagate any faster than the speed of light. The Einstein-Podolsky-Rosen, or EPR paradox, introduces one of the most mysterious ideas in quantum mechanics: quantum entanglement. Here's the idea. Two particles interact briefly, they influence each other so that their properties are somehow connected, and yet we refrain from measuring these properties to preserve quantum uncertainty. Quantum mechanics requires that we describe the particle pair with a single combined wave function that encompasses all possible states for both particles. We call such particles an entangled pair. Now, according to the Copenhagen interpretation, any measurement of one particle automatically collapses the entire entangled wave function and so affects the results of measurements of the other particle. That's an influence that could, theoretically, be transmitted instantly across any distance, and even back in time, violating locality and possibly violating causality. Einstein et al. Thought this was very silly. They thought that every spatial point in the universe must be real and physical and defined by knowable quantities, local hidden variables, that could affect each other no faster than the speed of light. The argument between Bohr and Einstein felt a bit philosophical at the time, but in 1964, Irish physicist John Stuart Bell proposed an experiment to resolve the debate. It involves entangled electron and positron pairs. When spontaneously created from a photon, these particles will always be spinning in opposite directions to each other. However, until measured, we can't know which direction either is spinning. We just know that they're opposite each other. Their wave functions are therefore entangled. Measurement of the spin of one of these particles tells us the spin of the other, no matter how large the distance between them. But in quantum mechanics, measurement actually affects the thing you're measuring. In the case of quantum spin, that measurement effect is especially weird. We define spin direction according to the spin axis. That axis can point in any direction. But to measure spin direction, we need to choose an axis to align our measuring device. We always find that the observed quantum spin aligns itself with our chosen measurement axis. If we choose to measure vertically, the spin will turn out to be up or down. If we measure horizontally, it'll be left or right. Measurement forces the alignment of the measured particle. But how does this affect the spin of its entangled partner? The answer would settle the Bohr-Einstein debate. Let me explain. Scenario 1, if Einstein was right. Imagine the response of each particle to all possible spin measurements is encoded in each particle at the moment of their creation, as hidden variables local to each particle. Nothing we do later to one particle will then affect the other. When we later measure the spins of both particles, there will be a correlation in the results because the particles were once connected, but there'll be no correlation due to our choice of measurement axis. Scenario 2. Bohr was right. What if, between creation and measurement, the electron and positron only exist as a wave function of all possible states? In that case, measurement of one particle's spin should cause the entire wave function to collapse, to take on defined values. Both particles should then manifest opposite spins along whichever axis we choose for one of the particles. That should lead to a correlation between our choice of measurement axis for the first particle and the spin direction then measured for the second. This is exactly the spooky action at a distance that made Einstein so uncomfortable. So John Stuart Bell figured out a set of observable results, the so-called Bell inequalities, that we'd expect to see in the case that Einstein was right and quantum mechanics needs local hidden variables. But if an entanglement experiment violates the Bell inequalities, then local realism is also violated. By the way, Veritasium describes this experiment in much more detail in this video. I recommend you check it out. It's a tricky experiment because entangled quantum states are hard to produce, but even harder to sustain. Any interaction can destroy the entanglement. But in the early 80s, French physicist Alain Aspect succeeded. Instead of looking at the entangled spins of an electron-positron pair, he used photon pairs with entangled polarizations. Polarization is just the alignment of a photon's electric and magnetic fields. But the principle is the same, and Aspect found that there was a correlation between the choice of polarization measurement axis for one photon and the final polarization direction of its entangled partner. The Bell inequalities were violated. The experiment was even set up so that the influence had to travel between the photons at faster than the speed of light. Since then, many experiments have verified this result over larger and larger distances. The instantaneous influence has been observed over many kilometers at this point. The delayed choice quantum eraser, which we already covered, is yet another example of this strange result. It's now been thoroughly confirmed that the Bell inequalities are violated, suggesting that the wave function cannot have local hidden variables. So does this confirm the Copenhagen interpretation and kill both locality and realism? Do we live in a peekaboo universe that vanishes into quantum abstraction when we aren't looking at it? Are babies really better at quantum mechanics than Einstein? Well, not so fast. The results of these entanglement experiments do seem to violate local realism, but that may mean a violation of realism or just of locality. In fact, it was Dr. Bell's opinion that the violation of his inequalities disproved only locality. Realism could be salvaged. Non-locality requires that entangled particles affect each other instantaneously. That sounds blasphemous to anyone who accepts Einstein's theory of relativity. However, non-locality and relativity can actually be perfectly consistent. Relativity requires that causality is preserved, so no faster than light information flow. But none of these entanglement experiments allow any real information to be transmitted between particles. It's only possible to see the influence between the entangled partners after measurements have been made and those measurements are compared. Just as we saw with the delayed choice quantum eraser, the universe seems to conspire to avoid the paradox of information traveling faster than light or backwards in time. The Copenhagen interpretation remains consistent with all quantum observations. Niels Bohr's peekaboo universe may be the universe we live in. However, realist and hidden variable interpretations are also consistent as long as they abandon locality. For example, entangled particles may be dimensionally connected by Einstein-Rosen bridges, wormholes that allow instantaneous contact even between great spatial separations. Also, the de Broglie-Bohm pilot wave theory works by assuming realism and non-local hidden variables. There's even a way around all of this without sacrificing realism or locality. That's the many worlds interpretation. We'll get back to these in an upcoming episode of SpaceTime. Last minute announcement. Tomorrow night, Thursday the 22nd, is PBS Nerd Night at the YouTube Space in New York. Myself and several PBS digital hosts will be talking about nerdy stuff. Link in the description. Okay, last week we talked about self-replicating spacecraft and why it may be surprising that none have found their way to Earth. There was lively discussion in the comments. Let's see what you had to say. Daniel Oberly and others point out that a von Neumann probe may be in our solar system, but be well hidden. Would we ever even see a single probe if it didn't want to be seen? Okay, so the same statistical arguments for von Neumann probes tells us that if we expect one, then we expect lots. Okay, so given that, we can't expect all probes to be equally cautious. Remember, these things may be created by civilizations only slightly more advanced than our own, by a few centuries perhaps. Humans are not on track to extreme cultural enlightenment over that timescale, but we are on track to some unthinkably powerful technological advancements. There's no good reason to insist that a species that can reach an interstellar capable state will be highly culturally evolved, let alone to insist that all will be. So even if there are invisible probes hiding behind the moon, put there by some utopian prime directive-obeying civilization, there should also be probes blundering through the solar system with no concern about being noticed. Strophy Cornego and others wonder if life might be the ultimate von Neumann machine. You know what? That's not entirely crazy. We're on the verge of creating synthetic life ourselves. This type of miniaturization may indeed be the most sensible for building self-replicating explorers. The question then becomes, if Earth was seeded once, was it seeded only once? Again, if one von Neumann machine entering our system is likely, then lots are likely. All life on Earth pretty clearly descended from the one self-replicating molecule type. That said, Other later invaders may have failed to find purchase on this planet once the first had come to dominate. But if these artificial panspermianic seeds are common, then we should expect to find them in space and on other planetary surfaces. That's hard to do, but there may be a way. Born Stella asks, do you want Reapers? Because this is how you get Reapers. Why do they have to be Reapers? Why can't they be Autobots? The weird rules of the subatomic world are very, very different to those of the familiar large-scale universe. A huge outstanding question is when and why does the weirdness of quantum mechanics give way to classical physics? One answer to this question suggests that the entire universe is so much weirder than we imagined. Or should I say, the multiverse. One of the strangest features of the quantum description of reality is the idea of superposition. We can't describe the most fundamental building blocks of our universe with defined singular properties. Instead, they seem to behave as probability clouds of all properties they might have were we to try to measure them. Mathematically, this is encapsulated in the wave function of a quantum particle or system of particles. The best illustration of why we need to describe the quantum world this way is the famous double-slit experiment. We did an episode on it, check it out if you aren't familiar. But to summarize, a stream of photons or electrons or even molecules travels from some point to a detector screen via a pair of slits. These particles arrive at the screen distributed like the interference pattern you would expect from a simple wave. Quantum mechanics very successfully predicts this result by describing each particle's journey as a superposition of all possible trajectories. In other words, the particle simultaneously takes all possible paths, which means it passes through both slits. It tries out all histories between launch and landing, and those many maybe histories somehow interact with each other to determine the most likely final destination when a measurement is made. In a sense, different possible superposed histories appear to converge on one final outcome, but what causes that convergence? In the original Copenhagen interpretation of quantum mechanics, the act of measurement was thought to collapse possibility space into a single reality, at least with respect to the measured property. It collapses the wave function. That collapse signifies the transition between the quantum and classical realms. One of the founders of quantum mechanics, Erwin Schrödinger, found this ridiculous, and he proposed his famous Schrödinger's cat thought experiment to highlight the absurdity. It goes like this. A cat is in a box with a flask of poison. A machine containing a radioactive element is set to shatter the flask in the event that the radioactive element decays. If that happens, the cat dies. That radioactive decay is a purely quantum process, and so until it's observed, it exists in a superposition of states. It has both decayed and not decayed. But doesn't that mean that the entire macroscopic system attached to that quantum event is also in superposition? If so, then the cat should be simultaneously alive and dead until we open the box. But why can't the cat collapse its own wave function? And from its point of view, is the physicist outside also a quantum blur until the box is opened? And what about the entire rest of the universe that's not currently being observed by physicists or cats? Many adherents to Copenhagen now have a more sensible resolution to the paradox of Schrödinger's cat. It's that quantum superposition doesn't extend to macroscopic scales. It disappears when different quantum scale histories diverge. This is called decoherence. When the wave functions describing quantum systems overlap sufficiently, in other words they are coherent, it's possible to get interference in the double-slit experiment and spookily correlated quantum entanglement measurements. But when these systems interact with their environment, coherence is lost and parallel histories fall out of alignment. They can no longer interact with each other. By the Copenhagen interpretation, we might say that the universe chooses the final outcome of all of those histories. It doesn't exactly choose a single history, instead it chooses an end result, say particle location on a screen, or cat alive or deadness, based on those histories. If a larger number of possible histories lead to a given result, then it's more likely that the universe will select that outcome. The Copenhagen interpretation says that this selection happens in a fundamentally random way. The universe plays dice, even if the dice are weighted towards certain results. It is what we would call a non-deterministic interpretation because there's no underlying predictability behind the selection. However, there is another way to interpret the transition between the quantum and classical worlds. What if the wave function never collapses? If we can imagine a cat in a superposition of states, alive and dead, why stop at the cat? What if the family of possible states extends beyond the radioactive decay, beyond the cat, and includes the observer, and indeed the entire universe too? If we open the box and find that the cat is alive, it's because we are part of an entire quantum timeline in which the radioactive decay and subsequent poisoning never happened. But there's an equally valid timeline in which it did, and another version of us experiencing that. This sounds outrageous, but it's a very serious interpretation of the mathematics of quantum mechanics. It was proposed by Hugh Everett in his 1957 PhD thesis entitled The Theory of the Universal Wave Function. It's come to be known as the many worlds interpretation. To outline the idea without killing so many cats, let's talk about what this means in the context of the double-slit experiment. The Copenhagen interpretation tells us that the superposition of particle trajectories, of histories, merges into the single timeline of the observer's reality. Many worlds says this merging never happens. Those alternative histories continue, and we find ourselves in just one of those timelines. Which one? Well, they're all equally likely, but some look very similar to each other. For example, many histories lead to photons landing on the bright bands of the interference pattern, and very few to the dark bands. We tend to find ourselves in the more common families of histories. This is a pretty crazy notion. The many worlds interpretation invites the idea that reality splits into different branches every time quantum states diverge into different possibilities. For example, at every particle interaction everywhere in the universe. This would lead to an unthinkably large number of alternate timelines, or worlds, that contain all possible realizations of this universe since the Big Bang. It seems extravagant to propose uncountable, eternally branching universes just to get out of collapsing a wave function. It's like building an entirely new house to avoid doing the dishes. But remember, the Copenhagen interpretation itself proposes multiple worlds in the superposition of paths or properties of a quantum system. Both many worlds and Copenhagen create alternate realities. It's just that Copenhagen merges them into a single timeline with its wave function collapse. The superposition of states of many worlds can be thought of as overlaid histories, slices of a universal wave function that diverge from each other as the universe evolves, but none ever vanish. Many worlds may in fact be the more pure interpretation of the mathematics of quantum mechanics because there's nothing in that math that requires the collapse of the wave function. So many worlds is more economical in the number of unsupported concepts it adds to quantum mechanics, even if it isn't particularly economical in the number of universes it predicts. Now, Everett's idea wasn't taken too seriously when it was first proposed. That may have been in part because he wasn't a well-known physicist. He was just a graduate student who all but disappeared into military research at the Pentagon right after graduation. But another point of resistance must be the overwhelming existential crisis induced by the idea of near-infinite versions of oneself. Many worlds may imply that every possible version of you exists out there. You're just the one who happens to be experiencing this branch of reality. every other possible life path, including those branching in different directions from every decision you ever made, may be just as real. In fact, each may be real in vast multitudes. There's no more evidence for many worlds than there is for other mainstream interpretations of quantum mechanics. And it is somewhat mainstream these days, with many noted physicists being swayed by its parsimony, its economy of ideas. But it remains an interpretation, and so although it is supported by the incredibly successful mathematics of quantum mechanics, it has not yet added a prediction that might distinguish it from other equally supported interpretations. Nor is it complete in its explanation. There are some ideas about what's really happening when these neighbouring coherent histories interact, or why the wave function translates to probabilities the way it does, but they are far from generally accepted. Unlike Copenhagen, many worlds is a deterministic interpretation. Any given timeline is a predictable chain of cause and effect. It explains the apparent randomness of quantum mechanics with a sort of observer bias. All possibilities are chosen at every junction, and we just happen to be seeing the one that happened in the branch that we occupy. That adds a second possible cause for philosophical unease. In a purely deterministic universe, what happens to free will? If we're going to make all possible decisions anyway, why sweat any given choice? Well, sure, but of all those countless future branches of reality, some are going to be pretty amazing. Think of it as a choose-your-own-adventure, and steer this version of you towards one of the more awesome many-world branches of space-time. Wow, guys, do you know who this is? This is Diana from Physics Girl right here on SpaceTime. Hey,
it's
Diana.
cool to be in space here.
Yeah, it's nice, right? One thing I love about your show is all of the crazy awesome experiments you do. They are so much fun. That thing with the water vortexes blew my mind.
You don't do a lot of experiments on your show.
We could do experiments.
Okay, well then I have a challenge for you. I want to challenge you to prove that the Earth is round using an experiment.
Ooh. How long do I have?
You've got a year, starting now.
Challenge accepted. One thing I really like about Physics Girl is it explains complex stuff in such understandable ways.
I try.
But I'm a kind of jargony kind of guy. I love those long, sciencey words, but it's hard to keep track of them sometimes. So I have a challenge for you.
Okay.
I would love you to do an episode in which you explain the 5 most jargony and commonly encountered modern physics words in simple English.
Done.
But I want you to use only the 1,000 most common words in the English language to do that.
That's gonna be a little harder.
Yeah.
But challenge accepted. So keep watching PBS Space Time to make sure that Matt follows up with that challenge.
And keep watching Physics Girl, because we're going to hold you to that, Diana. This episode is supported by the Great Courses Plus. One of the strangest experimental results ever observed has got to be that of the single particle double slit experiment. It's one of the most stunning illustrations of how the quantum world is very, very different from the large-scale world of our physical intuition. In fact, it hints that the fundamental nature of reality may not be physical at all, at least in any sense that we're familiar with. Let's start with the familiar. In fact, let's start with a rubber ducky. It bobs up and down in a pool, causing periodic ripples to spread out. Some distance away, those waves encounter a barrier with 2 gaps cut in it. Most of the wave is blocked, but ripples pass through the gaps. When the new ripples start to overlap each other, they produce this really cool pattern. It's called an interference pattern. It's due to the fact that in some places, the peak of the ripple from one gap stacks on top of the peak from the other gap, making a more extreme peak. You also get more extreme dips when 2 troughs overlap. We call this constructive interference. But when the peak from one wave encounters the trough from another, they cancel out. leaving nothing. Destructive interference. So we have these alternating tracks of wavy and flat water. Any type of wave should make an interference pattern like this. For example, water waves and sound waves, but also light waves. This double-slit interference of light was first observed by Thomas Young back in 1801. A source of light passing through two very thin slits produces bands of light and dark stripes, alternating regions of constructive and destructive interference on a screen. Of course, we now know that light is a wave in the electromagnetic field, thanks to the work of James Clerk Maxwell a century later. So it makes perfect sense that it should produce an interference pattern, right? But wait, we also know that light comes in indivisible little bundles of electromagnetic energy called photons. Einstein demonstrated this through the photoelectric effect, but his clue came from the quantized energy levels of Max Planck's blackbody radiation law. Check out our episode on this for the details. Okay, so each photon is a little bundle of waves of electromagnetic field, and each bundle can't be broken into smaller parts. That means that each photon should have to decide whether it's going to go through one slit or the other. It can't split in half and then recombine on the other side. That shouldn't be a problem as long as you have at least two photons. One photon passes through each slit, and then the two photons interact with each other on the other side and produce our interference pattern. But here, we get to one of the craziest experimental results in all of physics. The interference pattern is seen even if you fire those photons one at a time. Well, let me back up a bit. The first photon is detected as having arrived at a very particular location on the screen. The second, third, and fourth photons also. They deliver their energy at a single spot, and so they appear to be acting like particles of well-determined position. But check it out. If you keep firing those single photons, you start to see our interference pattern emerge once again. By the way, Veritasium actually conducts this experiment in his excellent series on the double-slit experiment. Really worth a look. This is so bizarre. This pattern has nothing to do with how each photon's energy gets spread out, as was the case with the water wave. Each photon dumps all of its energy at a single point. No, the pattern emerges in the distribution of final positions of many completely unrelated photons. How can that be? Each photon has no idea where previous photons landed or where future photons will land. Yet each photon reaches the screen knowing which regions are the most likely landing spots and which are the least likely. It knows the interference pattern of a pure wave that passed through both slits equally, and it chooses its landing point based on that. It turns out that the photon isn't the only thing that does this. Shoot a single electron through a pair of slits and it'll also appear to land at a single spot on the screen. But fire many electrons and they slowly build up the same sort of interference pattern. This crazy effect has even been observed with whole atoms, even whole molecules. Buckminster fullerene. Buckyballs are gigantic spherical molecules of 60 carbon atoms and have been observed to produce double-slit interference under special conditions. We have to conclude that each individual photon, electron, or buckyball travels through both slits as some sort of wave. That wave then interacts with itself to produce an interference pattern. Except that here the peaks of that pattern are regions where there's more chance that the particle will find itself. It looks like a wave of possible undefined positions that at some point, for some reason, resolves itself into a single certain position. We also saw this waviness in position when we talked about quantum tunneling. In fact, several quantum properties like momentum, energy, and spin all display similar waviness in different situations. We call the mathematical description of this wave-like distribution of properties a wave function. Describing the behavior of the wave function is the heart of quantum mechanics. But what does the wave function represent? What are these waves of, or waves in? Let's start with what we do know about the double slit result. We know where the particle is at both ends. It starts its journey wherever we put the laser, or electron gun, or buckyball trebuchet, and it releases its energy at a well-defined spot on the screen. So the particle seems to be more particle-like at either end, but wave-like in between. That wave holds the information about all the possible final positions of the particle, but also about its possible positions at every stage in the journey. In fact, the wave must map out all possible paths that the particle could take. We have this family of could-be trajectories from start to finish. And for some reason, when the wave reaches the screen, it chooses a final location. And that implies choosing from these possible paths. So what causes this transition between a wave of many possibilities and a well-defined thing at a particular spot? Within that mysterious span between the creation and the detection, is the particle anything more than a space of possibility? Okay, we're adding more questions than we're answering. We still didn't figure out what the wave is made of. In fact, the answers aren't known, but the various interpretations of quantum mechanics do try. Let's talk about the view favoured by Werner Heisenberg and Niels Bohr, who pioneered quantum mechanics at the University of Copenhagen in the 1920s. The Copenhagen interpretation says that the wave function doesn't have a physical nature. Instead, it's comprised of pure possibility. It suggests that a particle traversing the double-slit experiment exists only as a wave of possible locations that ultimately encompasses all possible paths. It's only when the particle is detected that a location and the path it took to get there are decided. The Copenhagen interpretation calls this transition from a possibility space to a defined set of properties the collapse of the wave function. It tells us that prior to the collapse, it's meaningless to try to define a particle's properties. It's almost like the universe is allowing all possibilities to exist simultaneously, but holds off choosing which actually happened until the last instant. Weirder, those different possible paths, those different possible realities interact with each other. That interaction increases the chance that some paths become real and decreases the chance of others. There's an interaction between possible realities that is seen in the distribution of final positions, in the interference pattern. That pattern is real, even though the vast majority of paths involved in producing the interference never attain reality. In the Copenhagen interpretation, that final choice of the experiment, of the universe, is fundamentally random, within the constraints of the final wave function. The theory of quantum mechanics produces stunningly accurate predictions of reality, and it's completely consistent with the Copenhagen interpretation. But this is not the only interpretation that works. There are interpretations that give the wave function a physical reality. Remember, we know that light is a wave in the electromagnetic field, and quantum field theory tells us that all fundamental particles are waves in their own fields. This may give us a more physical medium that drives these waves of possibility. And if you thought the Copenhagen interpretation was freaky, wait till we get to the many worlds interpretation, which we will, right here on SpaceTime. Thanks to the Great Courses Plus for sponsoring this episode. The Great Courses Plus is a service that allows you to learn about a range of topics from educators, including Ivy League professors and other teachers from around the world. Go to thegreatcoursesplus.com/spacetime and get access to a library of different video lectures about science, math, history, literature, or even how to cook, play chess, or become a photographer. New subjects, lectures, and professors are added every month. I've recently been exploring the Great Courses Plus quantum mechanics content. It's a thorough overview of a very complicated subject matter. With the Great Courses Plus, you can watch as many different lectures as you want, anytime, anywhere, without tests or exams. Help support the show and start your 1-month trial by going to thegreatcoursesplus.com/spacetime. Okay, let's look at some of the comments from our episode on the role of Jupiter in the formation of our solar system. Jason Blank asks, wasn't Jupiter almost a star? Well, the lowest mass stars are around 7.5% the mass of the Sun, while Jupiter is 1/10,000th of a solar mass. So it's not really all that close. You'd need around 75 Jupiters piled on top of each other to ignite sustained fusion in its core. A few of you wonder why we think Jupiter even needs to have a rocky core. Well, the Sun and other stars don't need rocky cores because they are massive enough for all of that gas to collapse by itself. There's a minimum mass that's capable of doing that. It's called the Jeans mass. It depends on cloud size, temperature, rotation rate, and composition. For typical interstellar clouds, the Jeans mass is quite a bit smaller than the Sun's mass, but still much larger than Jupiter's. For Jupiter to form its giant ball of gas, it needed a rocky core to start the process. That core may have dissolved since Jupiter first formed. Juno will figure that out by carefully mapping Jupiter's gravitational and magnetic fields. Bike Jake would like me to talk more about resonant frequencies. My pleasure. A resonant frequency is when two orbiting bodies have orbital periods that form a neat ratio of small integers. For example, for every one orbit of Jupiter's moon Io, its moon Europa orbits twice, and Ganymede 4 times. For every 8 Earth orbits, Venus does 13. These integer ratios maximize the amount of time that the planets spend in closest proximity. When these bodies are closest together, they have the strongest gravitational pull on each other, and that pull stops them from straying out of that resonant frequency. An imposter complains that the Jupiter episode was way too understandable. Don't worry, we got some incomprehensible content coming your way real soon.